how do we solve it? How do we find the antiderivative of integrals that involve roots? For example, square roots, cubic roots, or roots within roots. I'm talking about rational roots. So here, sometimes some integrals can be written in this form, not all of them. So here I just require that alpha, beta, gamma are all rationals and A and B are both reals. According to Chebyshev, if and only if at least one of the following condition is satisfied, then there is definitely an elementary antiderivative for integrals like this type of this form. Okay, so here's the proof. We're going to let x to the beta equal t, and then x is equal to t to the 1 over beta, and then dx is equal to 1 over beta t to the 1 over beta minus 1. Okay, now x to the alpha is equal to t to the 1 over beta raised to the power alpha. That is t to the alpha over beta. Now we're going to call this integral I. So I is now equal to t to the alpha over beta times quantity a plus bt. Again, x to the power beta is t, so this becomes bt to the power of gamma. dx is equal to this quantity, so it's 1 over beta times t to the 1 over beta minus 1 dt. Sorry, I forgot this. So dt. And now let's simplify this. So we're going to continue to write I down here. Just take out this coefficient 1 over beta. Integral, combine this term and this term. So just add up the index, this index and that index. So we have t to the power of alpha plus 1 over beta minus 1 times a plus bt to the power of gamma dt. All right. So in first case scenario, we say that if gamma is an integer, then we say that there must be an elementary antiderivative for this type of integral. Why is that? Now, because gamma is an integer now, could be positive integer, could be a negative integer, doesn't matter. If it's a positive integer, then this quantity will automatically become a polynomial. If gamma is a negative integer, then this quantity will just become a rational function. So by rational function, I mean it's when you have a polynomial on the denominator and maybe a polynomial, or it could be a constant on the numerator. So that's what I mean by a rational function. And now let's discuss this term. Since we assumed first case scenario, gamma is an integer, and we haven't assumed the condition of this term. So this term could or could not be an integer. In the worst case scenario, it could be a rational. So if alpha plus 1 over beta is irrational, then subtract 1 from it, it's still irrational. So this term, we can rewrite it as t to the power of rational. That is p over q, where p and q are both integers. Again, here, just this index, alpha plus 1 over beta minus 1, is equal to p over q. Don't worry about the precise value of p over q. Just so, because all we know that it can be expressed as a rational. That is all we need. Okay. And then, so what that basically means is that that is equal to t to the qth root. Raised to the power of p, by definition. Now, we can let t to the qth root equal to u, and t is equal to u to the power of q. And of course, we want to know dt. dt, of course, is equal to q times u to the power of q minus 1 du. Okay. Of course, this term is equal to, like I said, t to the qth root is equal to u. Therefore, this is u to the power of p. So that means we can simply replace this term by u to the p. So I is now equal to 1 over beta integral u to the power of p times quantity a plus bt. So a plus b times t. T is this quantity. So b times u to the q to the power of gamma dt. dt is this quantity times q times u to the power of q minus 1 du. Okay, now let's have a look at what's going on inside this integral. So u to the power of p is a polynomial. And a plus b times u to the q to the power of gamma. First case scenario, we assume gamma now is an integer. So like I said, whether gamma is a positive integer or negative integer doesn't matter. This term, this quantity, is going to be either a polynomial if gamma is a positive integer, or it could be a rational function if gamma is a negative integer. And let's look at this term. This term, q, is a constant. U to the power of q minus 1, of course, it's a polynomial. So when you multiply them all together, of course, you're going to either get a polynomial or a rational function in this case. If it's a polynomial, fine, great. We can easily solve it, easily find its antiderivative. If it's a rational function somehow, then we can simply factorize the denominator, then split it into a number of different rational functions, then find the antiderivative for each one of them. And that is not, there's no essential difficulty in doing that. So, first case scenario is now solved. I'll keep those, still be needing it. So, first case scenario proved. Second case scenario. So when alpha plus 1 over beta is an integer, what will happen now? So again, let's look at this term. So this is now an integer. Integer minus 1 is still an integer. Again, if it's a positive integer, then we have a polynomial. If it's a negative integer, we again have a rational function in terms of t. And let's look at this term. So in this case, we do not assume the precise value of gamma. So gamma could be an integer, or it could be a rational. So if it's an integer, fine, whether it's negative or positive. If it's positive, then it's going to be a polynomial. If it's negative, then it's going to be a rational function. So whether it's a polynomial or rational function, doesn't matter. If you multiply that with this, then it's going to again become a polynomial or a rational function. Again, there is no essential difficulty in solving that. So, worst case scenario, gamma is equal to a rational. So if gamma is rational, is equal to P over Q again, what will happen now? Now, this will become a plus bt to the P over Q, which is equal to the qth root of a plus bt raised to the power of p. And we will again let the qth root of a plus bt equal to u, and then a plus bt is equal to u to the q. And then we solve for t is equal to this a move to here and then divide by b. So it's u to the cube minus a over b dt now is equal to b still remains times q times u to the power of q minus 1 plus 0. That's constant, that's fine. Du. All right. We've got our dt. We've got our... This term is automatically fine. Don't worry about this term. Let's look at this term. This term, what is it equal to? Qth root of a plus bt is equal to u. And this is u to the power of p. So that's u to the power of p, actually. And so that means, like I said, this quantity is just this quantity. because we assume gamma is now a rational, so a rational, p over q, right? Integer over integer. So this is u to the p. So now my integral is equal to times u to the t. I should replace t with in terms of u in this case. So that everything is in terms of u across the board. So t is equal to this, b u to the cube minus a to the power of alpha plus 1 over beta minus 1 times this term. This term, like I said, is u to the p. U to the p dt. dt is this. b q u to the q minus 1 du. So let's look at this expression now. So like I said, this quantity is a polynomial in terms of u. Raise it to the power of some integer, could be positive integer or negative integer. So it's going to be either a polynomial or a rational function in terms of u. And times u to the p, that's just a polynomial. Times b over b under q times u to the power of q minus 1, that's still a polynomial. So when you multiply everything together, so it's going to either become a polynomial or a rational function in terms of u. So this is fine. Again, it's easily solvable in terms of finding its antiderivative. Okay, so case scenario number 2. What if alpha plus 1 over beta plus gamma is an integer? And then we can manipulate this expression by multiply something. I'll copy down this item t to the alpha plus 1 over beta minus 1 times an item t to the gamma times, of course, I have to divide by the same thing, t to the gamma. Copy down this item, a plus bt to the gamma dt. Now, I'll just combine those two terms. So alpha plus 1 over beta plus gamma minus 1. And then I'm going to rewrite this quantity as t under a plus bt. Because the bottom and top have the same power. So just this divided out to the power of gamma dt. Okay, now we assume that alpha plus 1 over beta plus gamma is an integer. So this is also an integer as well. So whether it's positive or negative, doesn't matter. It's going to be either a polynomial or... So this is going to automatically become either a polynomial or a rational function, depending on whether its power is positive integer or negative integer. So again, let's look at this. So in best case scenario, if gamma is a positive integer or a negative integer, and this is going to automatically turn into a rational function in terms of t as well. And when you multiply that by the polynomial in terms of t, it's going to again become a rational function in terms of t, which is easily solvable in terms of finding its antiderivative. In the worst case scenario, if gamma is irrational, so if gamma is some rational number, like p over q. P and q are both integers. In that case, what can we do about this? Again, likewise, the old method. Let's just let a plus bt over t. Copy down this item to the power of gamma is equal to, replace gamma with p over q and rewrite it as, what can we rewrite it as? Again, we have q at the bottom, so it's going to be the qth root of a plus bt over t raised to the power of p. Again, just like the old method, we will let the qth root of a plus bt over t equal to u. So this item is u. U to the power of p is equivalent to this quantity. Now, from this equation, raise both sides to the power of q. And we can simplify that and solve in terms of t. Solve for t, hopefully. So this will become a plus bt over t is equal to u to the power of q. So just simply rearrange the equation and solve for t. I'll just skip the steps and quickly just reach the final. From this equation, we can quickly solve. So just multiply t over to here and treat u to the power of q as a constant. Here, a constant of b in front of t. And then rearrange it, bring it to the other side. Here we only have a remaining, so t should equal to a over something. A over u to the power of q minus b, if I'm correct. Yes. Okay, then I'm going to continue right in here. Let's find out dt. dt is, of course, just apply the chain rule, differentiate in terms of u. Copy down the coefficient a. Of course, here is, this is in the bottom, so that means this quantity to the power of -1. So we have a -1 coming out. So negative a. Copy down that. Bottom we have u to the q minus b, quantity squared. That's just applying the standard rule of differentiation. And a chain rule, of course, we also have a q as a constant times u to the q minus 1. Just chain rule. And we're pretty much done. du, we're done with this one. du, okay. So now I have dt, and I also have this replaced in terms of u. Okay, now we can so that I'll just quickly go through. So t is now represented in terms of u. Just imagine. So from this integral, replace t with this quantity in terms of u and raise it to the power of integer. So we have a rational function raised to the power of integer. It doesn't matter if it's a positive integer or a negative integer. Case scenario number 3. It's going to be possibly going to be a rational function or a polynomial, doesn't matter. So this term is fine. How about this term? This term, like I said, I've represented this term with u to the power of p. So this term automatically becomes u to the power of p, which is, of course, a polynomial. And dt again, like I've just solved for dt in terms of u. Look at this. Still a rational function in terms of u. So now we have a rational function in terms of u multiplied by some polynomial in terms of u and multiply by some rational function in terms of u. Of course, which will again give us some rational function in terms of u. And of course, which is again easily solvable in terms of finding its antiderivative. So we're done with proving all the case scenarios. So, I mean, they don't have to be met at the same time. As long as one of them is met, or two of them, or three of them. So at least one of them is met. Then there is an elementary antiderivative for this type of integral. And if we want to prove because what I've done is I've proven the sufficient part of this theorem. But I haven't proven the necessary part of the theorem. So that means if none of these conditions is satisfied, then this type of integrals definitely does not have an elementary antiderivative. Which of course I'm not going to prove in this video because it's beyond my knowledge.